Let's take a look at Project 2, Part 3. This corresponds to Lesson 8 of Algebra 2b. So we are revisiting the equations that we looked at for the Project 6 portion, Lesson 6 portion, the first day of this project. We're going to revisit those equations and we're going to figure out whether they're invertible, and if so, what interval they are invertible for. And then we're going to solve them for different values. Sounds like a lot. This will actually be kind of a quicker section, especially compared to Lesson 6. So going through them, if you remember, our first formula for our spell from Lesson 6 was the Luke, I am your father spell. Kind of a cute name. Anyway, so this was our spell. And our question is the function invertible for the domain negative infinity to positive infinity? So notice that this is a quadratic. It doesn't really look like one, but if I were to rewrite this and separate my terms, 3/5 x squared plus 18/5 x plus 8, now it looks a little bit more recognizable as a quadratic. So in general, quadratics are not invertible for the whole domain of negative infinity to infinity. And that's because for a function to have an inverse, or to be invertible, it has to be 1-to-1. So every x, it has to have a unique x for every y. All right. Quadratics generally have a y coordinate, the same y coordinate appear twice, right? So two different x coordinates will have the same y. Let me show you what I mean. So I'm going to pull up a graphing tool. This is just Desmos, DESMOS.com. Simple graphing tool. It works for intermediate type problems. If you need advanced graphical functions, it's not going to be a good tool, but it works for our purposes here. So I'm just going to graph the parent function x squared. Okay, so here's my function x squared. Notice that y values appear twice. So if I kind of trace, and I know it's probably hard to see on your screen, but I've got this point and I'm tracing the y values of this function, the x and y values. For example, if I come all the way down to 1, when x equals, if I can get it, when x equals -1, y equals 1. When x equals +1, once again, y equals 1. So right there, I can see that y values do not have unique x values. So when we think about, for example, if you remember when we're trying to figure out whether or not something is a function, we do the vertical line test, right? And we say, you know, if I have some function that looks like this, or I guess it's not a function, some relation that looks like this, and I put vertical lines through the graph, it has to pass the test where this vertical line passes through only one point on your relation. And if that is true, it's a function, right? Notice that the picture I've drawn, each of these points, or each of these lines passes through 2 points on my relation. So I know this isn't a function, and that's called the vertical line test. Well, you can kind of think of, to figure out invertibility, we can kind of think of a horizontal line test, and let me show you what I mean. So once again, I'm just going to draw a basic parabola shape. So imagine that we're looking at something like this. So I'm going to call this a horizontal line test, and I don't think this isn't something that I've heard referred to in formal math classes, so I wouldn't go around calling it a horizontal line test, but I'm just calling it that for ease of understanding. So imagine I've got my parabola, and I pass horizontal lines through it, okay? And I'm going to say, all right, well, my function's invertible if y values have unique x values, all right? So notice that, you know, I've hit, by passing this horizontal line through, I've hit 2 y values, the same y value twice, and down here it's happened again. You know, for any line that almost any line that I pass through, I'm going to hit the same y value twice. And that means it's not invertible for the whole domain, okay? It's not invertible for the whole domain of negative infinity to infinity. So that doesn't mean that I can't restrict the domain and just say, all right, well, if I look at this particular piece, okay? So what I'm going to say is I'm not going to cut off a portion, but again, I'm going to restrict the domain. And I'm going to say, well, if you only look at this region, you know, if we only look at this region, this interval of the function, we can have an inverse there. So going back to that graph, let me show you what I mean. Let's say we keep x squared, and I say, let's just look at the values where x is greater than or equal to 0. So now I've shaded in x greater than or equal to 0. Okay? Notice that if I only look at the shaded region, imagine once again doing that horizontal line test that I described, but only in the shaded region. Now it would pass that test, right? If I ran horizontal lines through the bluish part of the graph, it would only hit one point on my function. So this part is invertible, okay? And what I've done is I've cut my parabola in half, right? I purposely planted that shaded region right at the vertex, okay? So the vertex, there are several ways to think about it. You can think of it as the point lying on the axis of symmetry. You can think of it as like the low point of a graph or the high point of a graph, or the point where it switches direction, the slope switches from negative to positive or positive to negative. I think we all have an intuitive or at least visual understanding of what a vertex is, and that's the important part. So again, notice that I've cut my function in half more or less, and I'm restricting the domain. So my new answer for this picture that I'm showing you would be, well, it's not invertible from negative infinity to positive infinity, but it is invertible if I look at x greater than or equal to 0. And notice that I include 0. Okay, so for x greater than or equal to 0. Another way of saying that in interval form would be it's invertible on 0 to positive infinity. And once again, we're including 0, so that'd be a closed bracket from 0 to positive infinity. So you're going to do the same thing when answering yours. You're going to have to figure out what is, you could graph this, all right? You could graph this and find the x value of the vertex, but we're going to do it algebraically. So let me show you what I mean. So this is not the same equation that you have. It's just a similar one, just like I had done in previous videos where I used a similar example to model an example for you. So this is a parabola. So I know it's not going to be one-to-one. So I'm going to have to restrict the domain and figure out where it is invertible. So just like in my picture where I cut my graph in half more or less, right? And then I just said, we're only going to consider this region on this from my lower bound of 0 to infinity. We're going to do the same thing here, okay? Only it's not going to be 0. We have to find h. And now you're asking, well, what's h? H is the x-coordinate, our general label for the x-coordinate of the vertex. And usually that's not just the vertex of a parabola. We usually describe that for other conic sections, but we'll talk about that later in class. So h is the x-coordinate of the vertex, okay? And it's going to be that lower boundary for the interval for which this function is invertible, okay? So in order to figure out what h is, we've already done this before from lesson 6, right? So h is equal to, oops, sorry about that. I don't know why that happened. H is equal to negative b over 2a. So remember, a, b, and c are the coefficients in my equation, where a corresponds to is the coefficient of the x squared term, b is the coefficient of the x term, and c is the coefficient, or is just the constant term, okay? So let's figure out what my a, b, and c are. So for this equation, don't forget the denominator. So in fact, let's rewrite this and separate each term. So I've got y equals 2 over 5 x squared plus 4 over 5x plus 10 over 5, all right? So now I'm going to use these coefficients to figure out the y value of my vertex. So negative b, here's b. I've got a, b, and c, a, b, and c. Negative b is going to be negative 4/5, and I'm going to divide that by 2 times a. A is 2/5. Okay, now I'm going to simplify. And we've done this before. You've already done this work in the first portion of the project because we had to put this in vertex form. So chances are you already have this. And once again, guys, I'm sorry, I don't know why the slides keep shifting like that. So I've got negative 4/5 over 2 times 2/5. I'm just going to simplify. Let's see here. So I'm going to simplify. First, I'm going to say 2 times 2 is 4. So I can rewrite the denominator as 4/5, right? So I've got negative 4/5 over 4/5. I could do the keep, change, flip thing to turn this into a multiplication problem instead of division, but hopefully it's easy to see that, at least in my case, I've got the same number. I've just got negative 4/5, then positive 4/5. This is going to simplify to negative 1. So for my answer, and yours probably will not end up in that format, again, this is just an equation I made up off the top of my head, okay? But I simplified. I found that my h is equal to negative 1. You'll do the same thing for yours. You'll take negative b over 2a, all right? And that means that my final answer is going to be, well, no, my function is not invertible from negative infinity to infinity, but it is invertible from negative 1 to positive infinity. All right, so this is the interval for which my particular example equation is invertible. All right, and you'll use the same means to look at yours. Note that you can do it algebraically, as I've just demonstrated. You could also do it graphically by graphing your equation and finding the x value of the vertex. So next they say, and we're looking at the same equation, use f negative 1, or use the inverse. This is just saying inverse. Use the inverse to find the solution to, and now instead of y equals, we've got 11.2. All right, so they've just turned this into a one variable equation and they want you to solve. So before you were trying to isolate variables, now you're solving for variables. We've taken it down to a one variable equation and we need to solve. So from the lesson 6, or the part 1 of this project video, I think that instruction should be ample to help you figure out how to solve from here. I'll get you started. I'm not going to do a model equation because, again, I think you guys can take it from here. But remember, we're trying to isolate x. So for example, my first step would probably be to multiply both sides of the equation by 5, right? So I'd have 11.2 times 5 on the left-hand side is equal to 3x squared plus 18x plus 8. Well, then I'd have to simplify a little bit, right? So 11.2 times 5, let's see, that'd be 56, is equal to 3x squared plus 18x plus 8. All right, from here, I'm just going to describe. I'm not going to solve the whole thing for you, but I will describe what you need to do. So I need to set this equal to 0, all right, because I am finding, the solutions I'm finding are going to be the zeros of the equation. So if I subtract 56 from both sides of the equation, you'll simplify that, right? You'll get 3x squared, 0 equals 3x squared plus 18x, negative 56 plus 8, that'd be what? Minus 48. So what do you do from here? How do you isolate x? You are going to factor, all right? You're going to factor this, and then you're going to come up with two solutions for x, okay? Once you factor this, you're going to come up with two solutions for x. One hint I'll give you, take a look at the coefficients for each term. See if you can reduce them if possible. Remember, you can only reduce if you can divide the same number by all three terms. So try reducing first, and then factor, solve for x. Once you get x, your x answers, right? So you'll get something and something. Compare them to your interval from the last question. Okay, so I don't know what your interval is, but you had some interval, some solution interval that looked like that, right? You're going to keep the answer that falls in your interval. So for example, okay, and again, this is an example, I'm making this up. If my interval, if you remember mine, I think was negative 1 to infinity. So if I ended up with x equals negative 10 and x equals 2, I'm going to trash this negative 10 answer because it doesn't fall within my interval. I want the solution that falls within my interval, so I would keep x equals 2. All right? So that's just an example. That's not your interval. That's probably not your solution. I don't actually know what the solution to yours is. All right, so again, I've gotten you to this point. From here, you're going to see if you can simplify the coefficients. You're going to factor. You're going to get your solutions for x. And then you're going to keep the answer that falls within your interval that you established in the last question. All right, let's move forward. The formula for the beam me up Scotty spell is, and they give it to us, and they want to know if this one is invertible. So I feel like I've already talked in detail about how to figure out if something is invertible, so if needed, please rewind. Shortly, I will just repeat. Invertible meaning it's one-to-one. Each y value has one x value. Each x value has one y value. Okay? Now, let's pull up our graph again and just kind of take a picture. So we have, what is it? I'm just going to keep that open so I can see what it is. We have the cubed root, which I don't know how to represent that using this calculator. I will do, I'm just going to do a square root one. It's not going to look quite right, but it'll work. So I'm just going to make up one as I have been doing. So I'm going to do x plus 4, put that under the radical. I don't know, over 5. All right, so notice that this isn't a cubed root function, but it's a radical and it's going to work the same way. So, all right, take a look at this. This is, or I'll even leave it to you, is this invertible? So picture that horizontal line test I spoke about. Would this pass both a vertical line test ensuring that it's a function and a horizontal line test ensuring that it's one-to-one? Or would you need to figure out a way to restrict the domain? All right, so again, I'm just kind of giving you a look at this. In fact, I'll go back to the beginning and kind of zoom out so you can kind of see a long-term behavior of this. All right, so look at this radical function. Is this one-to-one or not? And I'm just going to leave it at that for that question. Next, they want us to use inverse to find the solution to 2 equals cube root 3 plus 6 over 2. I am going to just solve this straightforward. I don't see that using this inverse property is going to make the solution faster or more efficient. So instead, I'm just going to solve this as normal. So, in fact, let me do my similar example. So say this is my similar example. All right, this is not the same one that you'll be solving. I'm just going to solve it outright. So, you know, I would multiply both sides of the equation by 2. I get 2 equals the cube root of x plus 5. I would multiply both sides of the equation, or I would raise both sides to 3. 2 times 2 times 2 is 8. So I get 8 equals x plus 5. And I'd subtract 5 from both sides of the equation, and I would get x equals 3. All right, this method was shown in your lesson. Contact me if you need assistance with it. Again, I'm showing this way because I think it was, you know, obviously kind of more straightforward. I think that way was just going to add up extra steps. The point of doing it was just because we are talking about inverses, it makes sense to use that method to find the solution. Okay. Moving forward, so again, they're just going through all of the spell equations that we looked at for the part 6 or lesson 6 portion of the project. So, once again, we're being asked, is this invertible? So once again, let's just use graphing. I think visually it makes it pretty easy to understand when things are invertible or not. So in fact, this time, you know, I've just been typing in kind of sample equations. This time I'll type in your exact one. So 9 divided by x over 2 plus 3. All right, let's take a look. So is this invertible? Would this pass a horizontal line test? No, right? I don't think so. So you would have to, once again, restrict the domain. We can do this one visually. and I'll show you what I mean. So we've already done an algebraic example of uh, how to do invertibility, right? We did that with the parabola. For sake of simplicity, I'm going to show you this way. Notice where, do you see how these numbers or these lines are both approaching the same line on x? We call this an asymptote. The value of that asymptote is going to be the bound for my interval. So what is the value of that asymptote? If I just kind of trace, I can see that right now x is equal to -5, x is -6. If I keep going upwards, you can kind of see that x is very slowly, I mean, depending on how you think about it, x is slowly approaching -6. So that's going to be the bound for this one, okay? So it's not invertible on -infinity to infinity, but it is invertible from -6 to infinity, okay? Find the solution for x equals, or excuse me, 6 equals 9 over x over 2 plus 3. Once again, this is something we kind of covered in our isolation of variables video. So I encourage you to watch that one if you need a little bit more help with this one. I think I do actually have a sample one set up. So let's go through this. So once again, I'm going to solve it straightforward, okay, just for simplicity. Alright, so to begin with, I am going to multiply the denominator by both sides of the equation. X over 4 plus 2, x over 4 plus 2. On the right hand side, my denominator cancels out. On the left hand side, I get x over 4 plus 2 times 8, and then I've just got equals 9. Alright, from here, I am going to distribute the 8. So 8x over 4 would just be what? 8 divided by 4 is 2. So I get 2x. 8 times 2 is 16. So I've got 2x plus 16 equals 9. Did I do that correctly? Yes. And then I'm going to subtract 16 from both sides of the equation. I get 2x. My 16s cancel out. 9 minus 16 is a -7. -7 divided by 2, I get that x equals -7 over 2. Alright, so you can approach yours a similar way. So now comes your short answer paragraph section. So which function or functions were or were not invertible? In a short paragraph, explain why these functions were invertible on -infinity to infinity or needed restricted domains. Identify at least 2 other possible restricted domains for this function. So, you can take whatever approach you want here. You can talk, there were cases where I was speaking specifically about the particular spell equation, right? If you want, just keep it to that. When you generalize things, like when you say, oh, this is true for all quadratics, or this is true for all radicals, it gets a bit hairy. There are almost always exceptions. So I think it would be better just to say, for this spell and the equation associated with it, it was invertible or was not invertible, and here's why. You can talk about just the pictures of the graphs that I pulled up. If you do that, be specific. Remember, when you're writing these short answer problems, don't speak like you're just talking to me and that I know what you're talking about. Act like you're talking to an audience that really doesn't understand you, like you're tutoring a student or a fellow classmate, all right? So again, explain what was invertible, what wasn't, explain why it needed a restricted domain. And then it says identify at least 2 other possible restricted domains for the functions. We took a specific approach to restricting domains, but when we say identify 2 other possible ones, technically, like for example the parabola one that I used, f of x equals x squared, we restricted the domain here, right? I mean, technically, it would just have still been true. You know, the function would also just be invertible. This was the interval 0 to infinity. Had we been given the question, you know, is the function invertible on, for example, 5 to infinity? If they said, is the function invertible on 5 to infinity? Well, the answer still would have been yes, right? So that could be an example of another possible restricted domain for the function. All right, so I hope this video was helpful. I'll see you guys next time.